evening. My name is Julia Doloff, and I'm a member of the UCSC Alumni Council and one of your Slugs and Steins volunteer organizers. With me is April Yee, also a member of the Alumni Council and another volunteer organizer. On behalf of the UCSC Alumni Association, I'd like to welcome you to our monthly speaker series, Slugs and Steins Lectures from UC Santa Cruz. Before we get started this evening, I will read UCSC's land acknowledgement. The land on which UC Santa Cruz is located is the unceded territory of the Awaswas-speaking Yupi tribe. The Ama Matsun tribal band, comprised of the descendants of indigenous people taken to missions Santa Cruz and San Juan Bautista during Spanish colonization of the Central Coast, is today working hard to restore traditional stewardship practices on the lands and heal from historical trauma. As many of you already know, our Slugs and Steins series engages a UCSC faculty member monthly in discussion with you, our alumni, friends, and family. We want it to feel just like you're back at UC Santa Cruz, sitting in class, but maybe with a drink in your hand and without an exam. Before we introduce our speaker, we'd like to know where you're joining us from this evening, who you're watching with, and when you graduated. So please take a moment to fill out a short poll that just popped up on your screen, and we will share the results when a majority of them have come in. All right, so a lot of you are watching by yourself or with someone else. Most of you are in California, but we do have some folks joining us from other places in the US. Got a lot of 2020 alums and 70s and 80s. A lot of Oaks and Rachel Carson alum, and quite a few of you are transfer students. So thank you so much for sharing that poll, taking that poll with us tonight. So tonight we are pleased to welcome Professor Marco Rolandi. Professor Rolandi is the Jack Baskin Engineering Chair and Professor in the Department of Electrical and Computer Engineering. He is also the co-founder and chief scientific advisor of Cruise Foam, which makes sustainable packaging solutions. Professor Rolandi's research focuses on bioelectronic systems and devices and biological control in regenerative medicine and synthetic biology. His work has been highlighted in the New York Times, the Washington Post, the BBC, and various other media outlets. In today's Slugs and Steins, Professor Rolandi will discuss machine learning-driven bioelectronics strategies to create personalized wound therapy that updates in real time depending on the wound stage. So with that, I hope that all of you have your Steins, because I've got your slug, Professor Marco Rolandi.
Hello, thank you so much for the introduction. Let me see if I can share my screen again. I just need confirmation that you can see my screen.
Yes.
Okay, perfect. All right, why don't I won't tell you the title since it was already discussed. So let me just tell you why we're working on wounds. The cost of wound care is $30 to $90 million a year for Medicare patients. These are mostly not the type of wounds that will get, say, falling off a bicycle or something like that. The biggest costs tend to be wounds that have to be treated in the hospital, for example. These unfortunately tend to be wounds that are chronic. They can last a long time. They can create big ulcers under somebody's foot, for example, and really have a big impact on the quality of life. So I'm sure we all seen wounds, and we hopefully all see wounds that actually heal. The medical community tends to look at these healing wounds through stages. These stages are somewhat arbitrary in that, like, it's just a way to describe where a wound is at. It's not that the wound knows that is in the proliferation stage or the remodeling. And from left to right, they go from as soon as the wound is created, the first thing that happens, the blood coagulates, and that's the hemostasis. Then there is the inflammatory stage. Inflammation is always seen as a bad thing, right? We take anti-inflammatory drugs to like stop inflammation for the pain and so on and so forth, like ibuprofen. However, inflammation is a necessary stage for anything in our bodies because inflammation means that specialized cells such as macrophages, what they do, they fundamentally clean up the wound in that they try to kill bacteria. If there's bacteria, they try to remove debris, so on and so forth. And after that cleanup happens, that's when the wound can rebuild itself, the skin can rebuild itself. And that happens in two ways. The first one is called proliferation. This is when the new cells start moving towards the wound and they move from the outside to the inside. And then the remodeling where like the skin starts really taking shape, and ideally that will happen without a scar. These four stages are pretty much agreed upon for the medical community, and there's a lot of interest in how a wound might go from one stage to the next, especially when it has to do with chronic wounds. Now, this work was mainly done in collaboration with Professor Gomez, a professor in applied mathematics. She's actually the lead PI in this particular paper. And what you see on the left is a kind of a schematic view of the stages, right? On the top left, there is a healer wound, and a healer wound goes through the stages. There's hemostasis, there's the inflammation, proliferation, and remodeling. The the canonical view of, say, a chronic wound, a wound that doesn't heal, is a wound that gets stuck in the inflammatory stage, which is this one here. Okay. So it never actually goes through the healing phase. And what that means is that like then the wound does not heal, it's chronic, and it stays forever, basically. Now, what Professor Gomez with Dr. Issaroff and Dr. Zlobina, uh, Dr. Issaroff is a physician at UC Davis, a dermatologist, and Dr. Zima is a biostatistician. What they found out looking at genes in the wound, meaning looking at the expression on RNA, because depending on different stages, different proteins are produced, and to produce protein, one has to have RNA. When they find out that a non-healer wound, rather than not going from the inflammatory stage to the proliferation stage, it actually goes to the proliferation stage, but somehow it oscillates back. And so it ends up in a vicious cycle where is inflammation, proliferation, and instead of remodeling, which is the green, then inflammation again. And when I started this talk, I said inflammation cleans up, and we all know how many people suffer from autoimmune diseases. Autoimmune diseases is when the inflammatory cells do not recognize our own cells, and so they destroy our own cells. And in this case, in the wound, what happens is that after proliferation stage, it goes back into the inflammatory stage and it starts destroying again. And so the wound gets bigger and then smaller and bigger. It doesn't actually show as much in size, but it's showing these oscillations in the expression of the genes, where we color coded them, where the inflammatory ones are like purple and the sort of like proliferative one are orange. I do have a question, and a few thumbs up will help. When I draw on this slide, can you actually see what I'm drawing with the red pen or not?
Yes, we see it.
All right, perfect. Okay, maybe three thumbs up. Awesome. So the question that we ask ourselves, and rather that um, this funding agency asks us to solve is, can we make a wound heal faster? Now, I started talking about chronic wounds. Specifically, this work is on acute wounds, meaning the wounds that will heal, but we wanted them to heal faster. And the reason behind it is because chronic wounds are very, very difficult problem. And so we started with something simpler, such as an acute wound. And if we can make them heal faster, we might find a way to actually control what the wound is doing and eventually apply this work to a chronic wound. And the specifically the funding agency that asked this question is DARPA. DARPA is the Defense Advanced Research Project Agency. I know you think of defense, we no longer have Department of Defense. We think of defense as like things related to war. But in this case, DARPA, among other things, invented the internet. In this case, what they really care for is to rehabilitate the soldiers, but also the veterans faster. Unfortunately, war is a sad reality. People get injured all the time, and wounds are a big problem in the battlefield. And so in this case, DARPA wanted us to look into this. The beauty of it is that with this kind of work, one can then heal wounds that are on a firefighter, a wound that are on somebody in a car crash, and eventually, hopefully, wounds that are on people that have chronic wounds that have been bedridden with ulcers and maybe they have diabetes and they have wounds, chronic ulcers under their feet, so then they can improve the quality of life. Now, a few years back in 2020, myself, Professor Gomez is the person in the middle. Professor Tedesco is a associate professor of electrical computer engineering with collaborators at UC Davis, such as Dr. Issaroff, as collaborators at Tufts University, Michael Levin. We were fortunate enough to receive about $16 million to do this kind of work. And eventually we received another $5 to $6 million from ARPA-H to continue the work. So today I'm mostly going to tell you sort of like an arc of the work we did, mostly the results from the past 2 years, because there was a lot of development at the very core technology in order to solve this problem. Before I do so, I just wanted to share that I do very little. I'm up there, but the reality is that like I just get to talk about this, where the people that actually did the work are all the people in this slide. And most importantly, one key personnel is Dr. Ashlan Kui, who's the project manager for this kind of work. And this is just a snapshot in time because we've had many, many people work on here. And most importantly, apart from the research, we also trained very many people that eventually ended up doing something. Now, what did DARPA wanted us to do? The easiest way to think about it is that they wanted to create a device, something that one can wear, okay? A device that would easily be placed on, say, somebody's wrist or where the wound occurs, but a device that is not just like a bandage, right? It's not a bandage with maybe some antibiotic on it. They wanted a device that would actually record what the wound is doing. So ask the question, is the wound in proliferation? Is the wound is inflammation? And then decide using a recipe whether we need to intervene or not, and whether we need to deliver a little bit of a drug or not in order to make the wound heal faster. Fundamentally, the way I see it is that what we're doing, we're creating a private physician for every person, where the physician, in this case, when the physician treats a wound, they would look at the wound, they would use their expertise to decide whether further analysis is required or not. And then with their expertise, they also decide if the wound needs treatment or not, and often they would provide a treatment. And this is exactly what we do. We monitor the wound. We use artificial intelligence in this case in order to decide whether the wounds need to be treated or not, and what kind of treatment, and when we deliver it. So the way I like to say is that we kind of democratize in healthcare because physicians are they're expensive. They have to move places. Where if one could deploy this kind of device around in areas that are maybe hard to reach, and the device is connected also to a physician that can monitor it, then all of a sudden a physician can cure 100 patients instead of say 5 or 10. And how do we go about it? This is kind of how the program was set up. And I'm sharing this because, sometimes one thinks about a scientist as ideas, and the ideas eventually become a research program. DARPA is a little bit different. They actually usually have a very specific goal. In this case, was to close the wound in 50% of the time. And they also are quite prescriptive of how to do it. Okay. So what I have here is like a schematic, like on the left is a wound that will close, let's say, in 7 days. And they want us to turn into a wound that closes in only 3 days and a half, for example. And they wanted us to do it in using three components that will get together. The first component that I will go with is what they call technical area two, which really what it is sensing. And like a physician, what we did, we used an optical approach. So we have a small camera mounted on the wound that takes pictures every hour or so. And these pictures are compared using AI with a large database of wounds and decide whether the wound is healing or not, and whether we need to intervene. Now, who decides that is this algorithm, is a neural net that is trained to understand whether the wound is healing or not. And eventually, what happens is that when we deliver a drug, or the system monitors the wound again and figures out, well, as the drug had a positive effect or a negative one. And the delivery of the drug happens in this technical area one, and I will tell you a little bit about it. It's a way to deliver that can be controlled electronically, because all of this is, of course, connected to a small computer that sits on the bandage, and the small computer also is connected to the internet or Bluetooth with a larger computer where all our databases sit, so on and so forth. Now, this is almost like a back to the future kind of problem where if you start if you start moving things around inside your body and making, in a way, I like to say, we shrink time, right? In that, like, rather than taking 7 days, it takes 3 days. Then our system needs to understand at what stage the wound is at. And so the way I'm thinking about it is that, like, it's really all about time. A normal wound, let's say, would heal in 7 days. More is likely is about 20 days. And so the first thing we need to know is, when we look at a wound, does this wound look like a wound at day 3, or does it look like the wound at day 4 or 5? Now, if the external time is day 3 and the wound looks like a wound at day 5, then we're happy, because it means it's healing faster. Now, if the wound looks like a wound at day 3, it's okay. Maybe we don't need to intervene, but we may not. Now, if a day 3 after the wound happened, the wound itself looks like another wound at day 1, for example, then we're in trouble. That means we need to do something. And that's what the planner comes in, and that's when, we decide when to intervene. And ultimately, the other question we need to ask is, how do we intervene, right? And they're like, does this wound need an antibiotic? Does this wound need a push of pushing the cells together? And we usually do so with a small current. Or does this wound need maybe like a wash or something else? And this is really the core, and I like to say the brain of the operation, because really the brain of operation is also driven by the brain of the project, and this is Professor Gomez. Despite the fact I am the PI on the project, but she's really the person doing this. Now, I'm trying to summarize fundamentally like 6 years of research in a slide. Now, keep one thing to keep in mind, that all of these algorithms and all this AI is only as good as the data you feed it. And it turns out there wasn't very much data in this particular area, so we had to look at a few things. Now, one thing you see here on the right is this data here is like in vitro data. So in biology, usually we start with in vitro research, meaning we just have cells, and we add different types of cells that represent what's in the wound, and we try to understand how do they actually mature. There are in vitro wound models. On the left here, we have an image of the camera. So we just started taking a lot of pictures of wounds, starting with the cell phone actually, and then these pictures got rated by real physicians, and then we put the pictures and the rating into this timekeeper to figure out what was going on. This data was fed to the planner, and the planner then decides when to intervene. That ends up the treatment control decides the intervention. Now, same with the timekeeper, the treatment controller needs to be fed information, knowing that if the wound is inflamed, do we use treatment A or treatment B? So we had to do a lot of in vitro work testing all of the drugs that we used in order to be able to tell the treatment controller what to send to the wound. And TA1, which is mostly what I deal with, is these devices. They're designed, they're microscopic devices, they're wearable, they have the ability to deliver drugs by controlling it with an on-off switch that is driven by a computer. That is sort of like the innovation on that side of things. Now, this is a prettier schematic. This ends up in, it was part of the last paper that we wrote on this last publication. And it has a little bit more of the system. So what you see here is a schematic of a wound. There is a camera. The camera was developed by Professor Teodorescu. There is actually an actuator, which are devices that I developed to deliver the drugs. And they deliver a drug and an electric field. No, an electric field doesn't mean that we're like doing electroshock, right? We also know cauterizing the wound, which is old school way to like clotting the blood by doing little shocks locally. What we do, it's more, we have like a battery, and what this battery does creates a small current of ions along the wound, and this current tends to carry with itself the cells. They need to position themselves in order to uh, heal the wound. What was one thing I've learned that was extremely fascinating to me, that wound, a natural wound will have a built-in current. So it's a tiny battery that drives the cells, and this is how the cells know where to go. It turns out that the center of a wound is the equivalent of a negative pole, say, of a 9-volt battery, and the outside of the wound is the equivalent of the positive pole. And there's always a voltage between the two that tells the cells where to go. And this is a process that is also called morphogenesis, that means generating shapes, right? Because the cells have a lot of information, but they need to know how to put themselves together in order to make new skin. Now, this is connected to the internet, and the internet connection does two things. The first thing it does, it runs all of this algorithm, which we call closed loop. Um, the algorithm is equivalent to a self-driving car fundamentally. Now, rather than looking at the road and looking at like the medium and the turns and the sign to steer left or right, what this does, it basically looks at the wounds as enough information to decide, hey, do we need to do this? Do we steer the wound left or right? This is fundamentally the same thing. It requires a lot of computing power, so that the actual computing happens outside rather than on the small device that has a battery and a small computer that decides what to do by receives information from outside. We also have remote monitoring that serves two purposes. The first one is for the patients to see what's going on, and most importantly, it serves the purpose of making sure that if something is going wrong, that the physician can monitor it. Okay. So how does all of this come together? What's interesting is that like I show you some kind of fancy stuff, so you might imagine something very slick and fancy, but the reality is that like when one does research, the first devices tend to be pretty rough. So the first one was kind of a black cube. It was fine, didn't do very well. One thing that we really figure out is that like we are not good at sticking this thing onto the wound model. So we started working with in vivo wound models. And so the biggest problem at the beginning was that this thing will fall off all the time. And so we learned that we could use, this was an innovation from our physician colleague, that this is a bandage that one can buy in a medical supply store. And the beauty of it is that it has this little ring, and the ring is designed to place another type of device. So we decided to design the device to fit into this ring. So the bandage was sticks, is designed to stick, it sticks where it's supposed to be, and then we can just put that. And eventually it would become a little bit nicer. And the final version, to be honest, does not have all this silicone. But another problem was that things get wet. Things get wet and in these in vivo models, and electronics and water don't like each other very much, and so we had all sorts of issues there, but this got fixed. And this is like an exploded view, which is a little bit nicer, and I can go through the elements. So um the case in itself here, it's all made with 3D printed material. I wanted it to be white to have an Apple look, but my optics colleague told me that if we made it white, the camera will go crazy inside. So I gave up to look for black. This is the miniaturized camera here with the lens. Uh, what you see here is a circuit board that's um, some information. It has some circuits. It has batteries. It also has LEDs, and one needs LEDs because once we put this thing on the wound, everything is dark, right? Then there is this element here is the actuators. Now, what you see here, these are little reservoirs, meaning they're little vials, if you will. Each one of them contains a different drug, or rather two different drugs, and they are delivered through these little capillaries, and eventually these will be in touch with the wound. Okay, and the capillary in the middle is our neutral or our negative pole, and the capillary outside are all connected to a circuit. And there's 8 channels. We can address each of them independently, depending on what needs to happen. This is the more slick version that looks a little bit nicer. You can get a scale bar here. The wounds we work with is about an inch. And this was a little bit nicer looking. And if you look it from the camera, this is the camera lens. These here, the low LEDs required for illumination. And then we can go to the next one, and we actually took a picture of his of his lug because we needed to show that obviously there's a lot of stuff between the camera and the wound, and we want to make sure that the image was accurate. And also what you see here are the little electrodes here that are designed to, these are the reservoirs they're used to deliver the drug. And this is a picture of the tissue itself with the camera on an actual real in vivo model. And what you see here are the reflection of the LEDs, but we can interpret this picture entirely once we have enough of them, and we can really figure out exactly what's going on with the wound. Now,
We
as I
do
said,
have one question that I think is pertinent to the last few slides.
yeah, go ahead.
Yeah, so Benny asks, how often do the bandages need to be swapped? Is the adhesive ever aggravating to the person's wound?
That's a it's something that we thought about a lot. Uh, we swap the bandages every 3 days, mostly because that is the standard of care. Meaning that if one goes to the clinic and has a wound, they would actually swap the bandage every 3 days. So we designed the bandage and the device not to change too much the habits of the physicians and the nurses. So these devices are designed to be swapped every 3 days. Now, we did not develop the bandage itself, not the devices. It's from it's from a medical company. It's used in the hospitals already. So we didn't notice any issues with the adhesive itself. It might happen, but I'm sure it's been tested and FDA approved, and so like we didn't notice any issues. Okay, so what we want to do is this. If you look here on the left, we said we want to close the wound faster. Now, we think of each wound to have a trajectory. So a normal trajectory is saying yellow, and what you see here is time, so it's a function of time. How much is healed? And basically 0% healed is there's a big wound, and then 100% is when the wound is 100% closed. So we want to move the wound from a trajectory where it's not healing very fast to a trajectory where it's healing very fast. And the way we do it is this interesting system where we take a picture of the wound, as I said. There's something called a deep mapper, which is one of these algorithms that Professor Gomez develops. And the deep mapper decodes the image, decides what's the stage of the wound, and then decides that, hey, in order to go to close faster, I need to actually go to a different trajectory. And this is really how the wound should look like. So the target stage, this is how I want the wound to look like. Then it encodes an image. There's the target image, and then it compares the two. And what it does, it basically like provides treatment until the actual image has reached the target image. Okay. Now, this is how the device looks like. What you see here in blue and red are the different substances that we deliver. In blue, it's a saline solution that is used to apply this small current to the wound. And in red is actually the drug that we decided to use. It's called fluoxetine. Well, most of you probably have heard of it, is actually Prozac. It turns out my colleague, Professor Issaroff, did a fair amount of research on how topical application, this is topical, not systemic, so it's not like taking Prozac through a pill. Topical application of Prozac actually closes wounds faster because one of the things that happen during wound remodeling, a lot of nerves are created, and Prozac is something that increases the concentration of serotonin in the wound. And serotonin is a neurotransmitter, in this case, nerves like serotonin. This is another picture of how the device looks like. This is this PDMS that told about. These are the capillaries they're used to deliver. These are the reservoirs. And it's designed because this basically is designed to take care of the thickness of the skin, right? Still a bit rough. It's not super in that like this is the first stage, but this is how it works. Um, Now, as I said, we deliver both a small current and this drug fluoxetine using a battery. Now, this is a battery that a computer turns on and off, depending on whether we need to treat the wound or not. On the left here, there are two poles of the battery are connected to two reservoirs with water. And on the left, this is the positive pole. On the right is negative. So what that mean, and opposites attract and positive same repel each other. What that means is that if this is positive, it's going to push positive things into the wound onto the other side. Turns out this drug named fluoxetine has the same positive charge. So if this is positive, what's going to happen is that it's going to push the fluoxetine into the wound. This is actually a well-known mechanism. It's called iontophoresis. And I actually had iontophoretic delivery of muscle relaxant when I had a big, I pulled my hamstring a long time ago when I was doing more sports than I do now. And one way to get the drug faster into the muscle was actually do this iontophoretic delivery. The difference for us is we're doing it in a much more compact device, and instead of somebody, let's say the physiotherapist turning the switch on and off, we actually have an AI-driven algorithm that decides what to do. This is probably not interesting. One of the things that we developed, which is kind of bizarre, but the kind of things they want us to do, and other colleagues are using as well, is we call it the chicken test. But since we use Latin words in like in vitro, in vivo, we call it impulum. Now, the reason for that is that we have to test these things before we put them on the wound. And you can test them in solution, but it's not very good. And it turns out the best and cheapest way to do it is to actually just buy chicken breast from Trader Joe's or Costco or whatever. We had many issues with chicken breast being thrown in the trash in the lab and then smelling a lot, but it worked out. And one thing I should have said that like these programs at DARPA, they usually have two or three teams competing with each other and against each other. And where there was a team of this program at Columbia, was a team at Pittsburgh. And after we did this chicken test, most people started using it as well because they thought it was pretty good. And it's kind of like I used to call it a dress rehearsal. So before actually treating an in vivo model, what we do, we have to make sure the internet works, we need to make sure the batteries work, we need to make sure the stuff doesn't fall off, all the wires are connected, and so on and so forth. So we really had to do that. There was a lot of management behind this. So this is the experiment itself. We start off with an in vivo model with the wound. Um, we have the first device from day 0 to day 3, the second device from day 3 to day 7, and then we use standard of care. Mostly because it would just take too many devices, and we decided, and we knew that at the beginning, what matters is really the first few days. This is how it looks like, and this is actually a plot as a function of time of the probability of each stage. And this plot comes from real data where the camera takes the images, and then what the camera does, it will decide, compare the images with other images, and say, okay, the beginning, the wound is in the hemostasis phase where the blood is clotting. Then it's going to the inflammatory stage, and eventually the inflammatory stage, which is the orange one, goes down, and it goes into the proliferative stage, which is the yellow one, and eventually it goes into maturation, as we just wanted it to do. The fact that we can take a picture of the wound and get these stages out, to me, is really mind-blowing. It really speaks a lot to what these algorithm Professor Gomez has done. So we treat the wound first, as I said, with a small current for first day, and then we started delivering this fluoxetine in the way I described. Um, Now this is probably the most important plot. We had like relatively proof of concept data, and like there's no statistical significance here yet. Uh, Remember that plot of heal that I showed before? So like this is a functional time, about 20 days. 0% is a raw wound, 100% is fully healed. Now, the gray area represent a typical control trajectory. And when we have these control wounds, they're represented by this gray dot. Now, the green dots are the wound that gets treated with this closed loop algorithm that's basically this personalized physician. And you see, especially here, all the green dots at day 5, between at day 5, right? They are more healed than the gray dots, which is the control. I mean, their treatment is actually doing something. Okay? And this is actually a cross section of a wound. What happens is that when everything is done, you can take a little bit of skin and you start looking at the edges, how much it has grown. And what matters here is that the treated one has thicker skin by about 50%, meaning that the treatment has actually worked. Now, that is where we're at right now. I know it seems to be not very much for 6 year of work, but there was a lot of work behind it. And really what matters is the people who did the work were all amazing. And as I said, this is a snapshot in time, and these are all the students that we graduated and postdocs and their whereabouts, as far as I can tell. And there's been a lot of really hard work behind this. And with that, I would like to thank my current group, funding from DARPA. The Army is a different project in ARPA H. And this is our current group picture, and you for your attention.
All right. Well, thank you so much, Professor Rolandi. We do have a couple questions, and I just want to remind folks to be able to enter more questions if you have them. The first one was related to the device that you were talking about, and Jessica asked, how come this device doesn't get in the way of scab formation or cause more inflammation?
Mhm. That's a good. So we looked into that. We picked materials specifically that will not. They're designed to minimize things like foreign body reaction or other scab formation. We haven't gone as far as really doing a full kind of study, but we did study what's called biocompatibility, in that we took before we put everything together, we took all of the materials. All these materials were part of a biocompatibility study where we actually look exactly at, if you have this material on the skin or under the skin, will that create what's called a foreign body reaction or a scab or something like that?
Mm,
Great,
thank
thank
you.
you. Someone asks, what if the wound is much larger than 5 centimeters?
Well, so this is, as I said, is a proof of concept. It was designed for like a sort of like a control in vivo model. We've actually designed a device recently that is more modular and is also more flexible, so it's a little floppy, and so we can make a bigger bandage that can be connected to more delivery points, and so there's definitely a lot of room for improvement when it comes to like being sort of like able to treat irregular wounds, wounds that are big, wounds that are, say, on an elbow or a knee, like where like, motion is also a challenge.
All right. Benny asks, you mentioned that you use something adjacent to iontophoresis. I can't pronounce that word, to drive ions into the wound. Would this interfere with implanted pacemakers or ICDs?
We haven't tested it yet, but I would be probably not. Unless the wound is right on the top of the pacemaker, I think would be unlikely. Also because we use very, very small voltages and very, very small currents to do this.
Hmm.
Patricia asks, does the electric current influence cell differentiation like in some of Dr. Levin's lab with the planaria?
Wow. We haven't gone that far yet. Um, like this work actually started from what DARPA calls a seedling. And in this seedling, we actually worked very closely with Michael Levin on looking at cell differentiation and how we can affect cell differentiation in stem cells using bioelectricity, which is what Michael does. The idea was that we could do the same in the wounds. Uh, Now we don't know, we haven't been able to study all the cells inside the wound to see exactly what happens. But when we do RNA analysis, which tells us the genetic makeup of the cells, we can tell that we can transform, for example, some of these inflammatory cells into pro-reparatory cells. There's these inflammatory cells called macrophages that can either inflame and destroy or repair, and we can definitely make the transition go faster.
Hmm.
I have
Lisa asked, oh,
I have to take a 2 minute break and I will be back. And I will have to take my
okay.
camera off real quick. Sorry.
Can you still hear us, or would you like us to pause
No,
completely?
just pause it for 2 minutes and I
Okay.
will be back in a few minutes.
Okay.
So if any of you have questions out there, you have 2 minutes to formulate your thoughts and put them in the Q&A.
Yeah, that was so fascinating to know that this type of technology is out there. I recently had a procedure and I had a wound that was less than 5 centimeters, and this would have been interesting to have that have for me to have had something like that to measure the wound because it actually did take longer to heal. I think partly because I also had to take blood thinners after the procedure. So I, I, I was going to ask a question related to that too. Like, what if someone's on blood thinners? Would that affect the length and, you know, capabilities of this device?
Yeah, very interesting. I wonder if they'll do like clinical trials someday if they get, far enough out there.
Yeah, these are really good questions. Very technical. And remember, if you are in the audience, you can upvote the questions that are interesting to you, and we'll ask those, we'll prioritize those questions. And the way you
Okay.
upvote a question, if you see the
Hello,
Q&A, you
can you hear
can
me?
see the thumbs up. Yep, we can
Yes.
hear you.
So I'm back. What I'm gonna have to do, I'm gonna have to transition real quick. So just give me a second. I'll need to
Mhm.
come back from a different device. And thank you for
Okay,
your
sounds
patience.
good. So like I was saying, to upvote a question in the Q&A box, if you see the up, you just tap on that and then it'll upvote the question.
Okay, you should Can you hear me?
Yes,
All
we
right,
Yep.
can.
perfect. All right.
All right. So there are several more questions. The next question is from Lisa. What ML technique did you use?
Ooh, that is a question I will have to ask my colleagues because she is the expert in this. I'm more on the device
Okay.
side of things of the equation. And Lisa, if you want an answer to that question, if you can send a note to the either to me or to the moderators, then I'm happy to forward it to Professor Bowles.
Thank
All
you.
right.
We have another question. Clearly, this is the beginning of a long process. Is there a short-term path that just uses cell phone camera technology to directly manually apply care?
That is something that we've been thinking about as well. And the first thing that we actually tried to do was exactly that, to use a cell phone and to basically have a small cell phone app that will recognize whether a wound needs treatment or not. And rather than having an automated device, just simply informing either the patient or the physician that something needs to be done to the wound. So we've been thinking exactly the same way.
Okay. Samyuk asks, I wanted to ask what led you to dispense the topical form of fluoxetine as opposed to other treatments?
This was entirely driven by my collaborator, Professor Issaroff. She's a distinguished professor of dermatology at UC Davis, and she's an expert and a pioneer in using fluoxetine for these treatments. And one of the reasons behind it is also that fluoxetine is a very small molecule, and for us, the smaller the molecule, the easier to deliver. So it was a combination of her being an expert in this area and having shown some really good results, and also that molecule being small, so that we can deliver it faster.
Great. So Joseph says one of the issues with wound care, of course, is clot formation. This is particularly a problem with skin grafts. Would it be possible to use this device on skin grafts?
Potentially. Uh, it sounds like a great application. We haven't tried it yet. As I said, we were just at the beginning, so we worked on a very controlled model. This is something that would be very interesting to look into, I'm sure.
Mm. Priscilla asks, as we know, wounds heal from the inside out. At what stage do you take the device off for final healing?
Well, one of this particular device was designed to touch the bottom of the wound, and so that's why we only kept it on up to day 7, so then like the wound could start closing faster. There's another device that is the new one that is flexible and conforms to the wound better, and it doesn't actually interfere with the healing itself.
Got it.
So David asks, so eventually bringing these into use at scale will call for collaboration with a company or 3 in the tech med industry. Has your team started looking at such a collaboration yet, or is it a little too early for that?
So as part of the program, the follow-on funding from ARPA-H, we actually had an entrepreneur in resident. His name is Jamie Tenedorio. I don't know if it was one of his picture was there, and so we started looking into that. It's still a little bit early. Requires a lot of work, and most likely what's going to happen, our minimum viable product, our MVP, is going to be something a little bit simpler. For example, a cell phone diagnostics or a device that delivers treatment but doesn't actually have a camera, because everything together gets a little bit complicated to produce a scale and go through the approval process, etc.
All All right, we have two more questions. One from Lori. Having looked at war wounds, they are quite big. How can this device be adapted?
As I said, we have a newer device that is much larger, and also like the way DARPA usually works is they wanna demonstrate that something can be done, and then they hope that the technology is functional enough so either people, either funding agencies are able to pick it up and then do uh, something with it. And the typical word at DARPA is moonshot, right? DARPA was created as ARPA when the Soviet Union put the first man on space because they wanted to participate in the human race, and one of the results was in the space race. One of the results was putting somebody on the moon, and then everybody else we haven't gone back, right? And that's kind of a similar thing where like it takes a lot of technology to then eventually scale this and apply to real world scenarios.
Peter asks, how would this work in wounds that need to be stitched together for dermatological procedures?
Um, it's interesting. We haven't thought about that, and I don't think we'll be probably that would not be a good a good a good a good a good one to use this particular device.
Mm.
That is probably the answer is like there's some wounds where they need to be stitched together, and that is probably not, this device is not appropriate for that product.
I see. Is there Varun asks, is there a research paper published on this work? And if so, is it possible to share the link?
Yes, there is. I cannot share I can share the link in 3 minutes because the reason why I have to get off because I'm driving my daughter from gymnastics to soccer right now. But if the link is actually the nice thing is that the paper is publicly accessible, and if one were to search Rolandi group in publications, the paper will show up. But I cannot but also if you have, I don't know how many more questions there are, I can share the link in 5 minutes once I get to the next location.
Okay, and I mean it's fine. We can send a follow-up email too with the link included to all the folks who attended. And we might be able to even put it in the YouTube channel in the description of this lecture. All right.
Yeah, and I think I found it, so I will pop the link in there, and I believe it's the right one. So
Oh, awesome. Thanks, Julia.
our last question right now is this device supposed to work with glued wounds?
I would say glue wounds fall in the similar category as stitch wounds, so it's not designed specifically in that case. I think the way I'm thinking about it, like, and I keep on thinking of scraped knees because I had many, as a kid. That is the kind of wound that I think the device will the kind of shape in which this device will work best, right? Something where the skin gets abraded away, and there's like blood and stuff, and there's the tissue needs to be restructured, but there's really no room to use stitches or glue to close it because the skin just is gone, right? You cannot just put it back together, and that it needs to regrow.
I see. There is one more question, and I have a personal question myself too. I recently went through a procedure and had a wound. It might have been glued together. I'm not sure. But I was curious if people on blood thinners, if the device would be affected by people on blood thinners. I mean, the time frame or anything else involved with the device.
That is really interesting. I haven't thought about it. But that actually is a really, really nice question because I think it might be a potential research direction. The point being is like the fundamental concept behind the device that every wound is different, and and every person is different, right? And even every wound on every person is different. And so the point is that it's adaptive, meaning that it adapts itself to what's happening in the wound. So, for example, let's say if one person went to surgery and it forgot to stop their blood thinners, right? And then there's this, usually the problem is more internal bleeding, but let's say the wound is not healing because of blood thinners, then in theory, the device should just do something, even if the device doesn't know that the person was on blood thinners, right? It's adaptive. And so whatever is happening that is impeding the healing of the wound, in theory, or at least the device is designed to take care of it.
Oh, interesting. All right. Thank you for that. The last question is this good for small burns?
Oh, that is amazing questions. I'm glad this is recorded because I'm gonna forget them. But yes, I don't know yet. As I said, is that we started with the simplest case, which is a controlled in vivo model of an acute wound, and burned wound is something that absolutely I would love to look into. And it just comes to mind, like I'm from Italy, and you know there was this big problem in the Swiss mountains where like a nightclub, caught fire, like lots of teenagers died and many were burnt. And so I think it would be really good to be able to develop the device in a way that could also take care of burnt wounds.
Oh, wow.
So we do have a couple more questions
couple.
coming in. Susan asks, what kind of wound is this device intended for currently?
Well, so as I said, this device was intended for acute wounds, specifically because that's what we use as a model. In the long term, ideally, we'll be able to do it on any wound.
Peter asks, do you need to do something special for wounds cycling between the inflammation proliferation cycle?
So we have not got that far yet, but that's something that we would absolutely love to look into for our future work.
Corbin asks, is there any plan to have more on-device processing so that the bandage can function more independently?
Can you repeat that question? Sorry.
Yeah, is there a plan to have more on-device processing so that the bandage can function more independently?
That is, yeah. So yes, that's something we're looking into as well. Especially because, well, for many reasons. One, because people might not have access to the internet everywhere. And we're looking into it. That requires some careful thinking on how to simplify the algorithms so the all of these AI algorithms tend to require a lot of computing and they're very power hungry, and a lot of power means heavy batteries, right? And so we're looking into it.
All right.
And I'm curious, what's next for your research? So you just did 6 years of research. What is the next phase that you're looking at?
Well, I don't. Well, it's complicated. I don't know. I don't know because the program we were working on just got canceled due to internal realignment, and so I'm not sure. I hope it can be something useful like wound healing, and we are looking for more funding. And I think what we have developed can be used for many other things, and so we're just looking and see what is the most important problem we can solve.
Gotcha. Well, hopefully you can find some funding for that.
Yeah. All right. Well, that was the end of the questions. So let's give a big round of applause to Professor Rolandi. Thank you so much for leading us in this great discussion tonight. Super fascinating. I look forward to hearing what is next and what will come of this more. So as Julia mentioned previously, my name is April Yee, and I'm the VP of Finance for the Alumni Council and one of the volunteer organizers for the Slugs and Steins lecture series. This talk was recorded and will appear in a few days on the UCSC Arts Lectures and Entertainment channel on YouTube. Our thanks also go to the staff of the Alumni Engagement Team and Special Events Offices who organized this webinar. So thank you to Shayna, Diana, Paulina, Nicole, and Kristen. And thanks to Mike Reapy and Kelsey Knox, who are also volunteer organizers of this series. Our next event is on Monday, February 9th. Our speaker will be Professor John Brown Childs, and we hope you'll join us then. In the meantime, there are other upcoming events that may interest you, and I'd like to highlight 3 of them. So on January 20th, Nurturing Difference, Parenting and Disability in a Careless Age is a book celebration and discussion in person at 6 p.m. at the Cowell Ranch Hay Barn on campus. January 21st is a CRAW lecture focused on science and technology, Sensing the Unseen, How Drones and Ground Sensors Reveal the Hidden Air Quality Impacts of Climate Change. And that's in person and virtual. In person takes place at the UCSC Silicon Valley campus with a 5:30 p.m. reception, and the lecture will be from 6 to 7 p.m. And then on January 27th, it's the 42nd annual Martin Luther King Jr. Convocation in person at the Santa Cruz Civic Auditorium at 5:30 p.m. So hopefully you can join some of those events. And there's also a calendar of what else is happening in January. So on behalf of the UC Santa Cruz Alumni Association, thank you for joining us, and please come back for our February Slugs and Steins. Thank you.